Hello, I'm going to be sharing my screen and stuff like that in a second. Just hold on. Remember to record again this time rather than figuring out like 10 minutes in and say, oh, yeah, yeah, I got to do this. Um, so, three different things actually we're going to talk about briefly. Hopefully, if you can't hear me properly, let me know. First of all, before we get anywhere. So, number one, uh, this Friday is the final of the Dear Data exercises. If you don't have a partner, I talked to I emailed Rami, but I didn't get he missed the meeting, the TA meeting this week. Rami is going to be hopefully posting if he hasn't already, posted the homework, the Dear Data 2As for you guys to review. And you should see your partner. If you don't see your partner, the policy was if you don't see your partner, you can't read their file, review somebody else's, right? It's unless we screwed up. If your partner didn't do the work, then they don't get the feedback, which of course means you're supposed to get feedback for 1B, which I forgot to double check on it. That's really my bad in the I'm not supposed to be doing that posting. I asked other people to do the posting, but I normally monitor things more closely. I was a bit myopic when it came to the two exams coming next week. The two exams are coming a week earlier than I thought they were for my other two classes. Um, so that being said, you hopefully will get some kind of useful feedback from your partners for 1B. We want to double check to make sure that there's safe feedback to give you. If the feedback says you suck, not very nice feedback to give you guys, right? If the feedback says if this was great because but this was wrong or you could have tweaked that, right. That's the whole point. We learn from the best. Some of the best teachers are failure or errors that we make from experience. Anyways, beyond that, so this Friday is Dear Data number 2. Today's lab is essentially just in development help. I wanted to get ahead of this thing first before we start talking about the in-class exercise now. Our sprints, I know I was always surprised every time it happens, and it happens every single term, and I don't know how to get ahead of it. People start panicking over sprint, or they don't panic enough. It's one of the two. So in Bit 2400, which most of you have not done with me yet, uh, I get this sort of wave of panic from students when either they get a wave of panic when they have the midway deliverable. So they have assignments every 2 weeks. And at the 1 week point, I say, hey, pass in what you've done so far. You should be up to this point. And so you either get one of two responses. You get people freaking out about the deadline when there's no marks involved in the midway deliverable, or you get people not caring, not submitting it, and trying to do it the night beforehand, and then saying it's impossibly hard to do this time. And that's, I was there too. I know how that goes. But the midway deliverables are just to keep you on track. The same thing with sprints. These sprints are not meant to be. There are marks involved, but they're not meant to be uh, fear-inducing or panic-inducing things. They're meant to be, this is where you should be approximately be, because we know how the development cycle goes. We know you'll get about 90% of the way there, and that last 10% will take up about 90% of your time, unfortunately. So what we're trying to do is get you ahead of this giant project we all, we're setting out to do. And what we want you to do is find out when there's horrible things that are about to go wrong early. So if you cannot get maps to work on in Vega Lite, we want to know that in week 1 or week 2, and for you to say, "Oh my God, maps don't work in week 1 or week 2," and then we figure out a workaround. We want you to have a project that works. Is it exactly the project you originally set out? Probably not, or maybe not. There are going to be things that you know, technological issues in the way, or you run out of time in various things. But we want you to have something that's usable and doable that you can evaluate. Even if it's not to the full extent of the system that you wanted, you're being effectively graded by the, not the aspirational quality of your work. But it's essentially based on effort, right? If you have something that stops your system, or there's a technological glitch along the way that we didn't expect, because everyone's doing different systems, doing different things. If you have a technological glitch along the way that we can't figure out or we cannot work around, that's not your fault. You're not going to lose marks for that. So Vega Lite doesn't allow zooming into the map on the fly. Fine. That's not your fault. We find workarounds for it, but you're not going to be graded based on that, right? Based on it being absolutely 100% perfect. There's a technological issue. Here is what it is. You state it in your report. You state what you learned, what you didn't learn. You state what went right, what went wrong. We're talking or you're being evaluated based on that journey, which involves, like, when you're doing design, you do a whole slew of designs. Not the final design is what you're being evaluated on. It's that journey. I want to see where that learning curve is, right? Not did you hit the perfect solution. It is, are you learning along the way? Same thing with programming. This is not a programming course. And that was part of the feedback I got. I think I already responded about this, but uh, this is not a programming course. It is part of the course for sure. It's in the course description, course outline, but it's not the be all and end all. It is a tool in your toolbox. And I know people get scared of this tool in their toolbox, but it's an important tool in your toolbox. It's just not the only tool in your toolbox. It's not the only point of this course. So in the lab today and for the rest, for the next two, with this one, here, and here. So next 3 weeks, it's just going to be essentially office hours, right? I will try my best. And by the way, Isaac, if Isaac's on the line here, I got the bonus question for homework 8 up and running, or at least most of the way there. And I've hit little occasions along the way when I went, oh, that's probably what's happening. So I got alerts working, they work fine. I have all these other things working, but anytime you spelled anything wrong, like I have one missed character in one part of my code in JavaScript, one missed character in the variable name. Didn't give me a warning, didn't give me an error. It just, nothing worked. And then you find that one character, you put that one little character into the word because you've spelled it wrong, and then everything started working. It is insane. This is why I hate JavaScript, but it is the problem. So I can have a look at your code if you want, Isaac. But for the rest of you, I want to have this extra time too. We can discuss how we can work around it. I can try and look at your code. I'll be doing it on the fly, so I'm not guaranteeing. I don't read it the way I read C++ because you don't get syntax errors. Most of the time you just get like, it doesn't work. Why not? For your projects, my big suggestion is, if you're not sure about something, have one member of your group peel off, let's say, do a little toy project, little toy example, just to make sure it does work. This is what we had as a problem. That's how I found out about this map issue with Vega Lite, was I did a little toy project just to see that I could zoom in or not zoom in. And I spent 5 hours trying to debug that thing. It was just some weird esoteric thing. I'm not expecting you to spend that much time on debugging things, but if you want to know how to do a map of Ottawa, have somebody do a map of Ottawa. Don't try and do your final project don't try and learn how to do things on your final project. You don't, I'm trying to think of a good example. Not a good example, but when you're learning to drive, you normally want to use the crappy car. You don't want to use the good car. If you have 2 cars at your house, you don't want to use a sports car. That's for damn sure. When you're learning to drive, you want like a minivan, right? You want something that it's going to be fine. If you bump into something, right? You're not learning to drive on a Ferrari, right? You're building something, you're learning. So when you're learning new things, you can build off a little sub project, test it out, make sure you understand how it works, then pull it into the main project afterwards. It seems slower, it's a hell of a lot faster because you don't know how things work until you've played around with it a bit. Okay. So lab today is checking out checking out your projects or helping you out with your projects or answering any questions you have. The homework due on Friday is the last of the Dear Datas. Again, no coding involved in that one. And then we're in the middle of these sprints. And the sprints are aim for something. If you don't get it all the way there, don't panic, but ask for help. I want you to be panicked enough that you ask for help or try and figure it out now. I don't want you panicked enough that you're freaking out that you're going to fail the course or anything like that on homework on project 5. It is meant to be a milestone to keep you on path. It's just keep plugging away at this thing. And the reason we needed these final sketches is I want to, you need to be able to put some kind of timeline, some kind of to-do list, a prioritized to-do list for how you're going about development. And that's what Project 5 and Project 6 are. It is just, can I get to some state where I can evaluate my system, have others evaluate 3 tasks through my system properly using the system. And if I need to walk them around and say like, oh, you can't zoom, but let's pretend that you can zoom, that's fine. But it does involve working well in advance. By the way, this is Agile development. If you ever heard of the term Agile development, we're not doing exactly Agile, but we're doing the proto-Agile development. Programmers are infamous for saying, oh, yeah, I'll do it later. And that you procrastinate and then you try and do it all at once and it bites you. Or you pick up too much at once and you can't do it all in time. Or you spin your wheels in some place by making little milestones along the way. They quickly learned, this is after my undergraduate degree, by doing little milestones along the way, like week by week milestones for how to code something, you end up making sure that you don't miss deadlines. It's human nature to try and either bite off more than they can chew or procrastinate. And doing these like week by week little sprints at a time motivates you to keep going, essentially. Okay, neither here nor there. Let's actually get to what we're looking at now. For drive link 13B, so go to the drive when you get the chance. I wanted you guys to look at your members of parliament. Your members of parliament are from different parties. They have a particular seat in the House. I think Justin Trudeau is about right here in Parliament. The Speaker of the House is over here. They're seated next to each other within their party, but each member of Parliament has a particular voting record, what they voted for on various topics. There's a wide range of topics that they have available to them. The question is, can we use a visualization to keep people accountable or make sure people are accountable? So there's too much data to show all at once. So we need to either filter or aggregate based on this. We have a whole lot of different votes for, let's say, same-sex marriage or legalization of marijuana or Planned Parenthood or name a topic, right? Environmentalism. Environmentalism is a great topic, right? That's not just one vote. You don't vote for the environment or not one time. It's a series of votes over your career that and how those votes affect, have an environmental impact. So the question is, can you come up with, let's say we magically are able to put numbers on some of these things so we can ignore that aspect, which is a nasty aspect. Like the text in the speech, does that amount to voting for the environment or not? We're going to ignore that thing. We're just going to say there are sometimes we have a piece of legislation that is voting for the environment. Sometimes it's voting against the environment, right? Keystone Pipeline, it's increasing the amount of oil production and transportation of oil. We're going to say it's against the environment. If you're talking about cap and trade or carbon taxes and stuff like that, it's presumably for the environment. We're just going to look at it that way. Can you come up with some way of showing how your member of parliament or how a party or whatever you want to do, different kinds of aggregation, by party would be aggregating items. Your individual member of parliament is not aggregation of an item at all. It's a single individual person, but their attributes are aggregated. Can you come up with different ways of visualizing parliamentary choices, if you will, to help you understand how your member of parliament is voting, how individual parties are voting for different issues? That's the question. And can you sketch up some of this stuff? So sketch it up, take a photo, throw it on the Google Drive, and let's see what you come up with. I'm going to give you about 10 minutes more on top of that, but figure out what somewhat kind of idea that you want with it. Because it is aggregation and filtering in its purest form. Do you have a drop down? Do you have select the seat to see who it is, for example? It's under MP Palooza, by the way, in case you're lecture 13B, MP Palooza. If you don't know what a palooza is, look up Lollapalooza and be, surprised about the history of rock concerts in my era. All right, we have nothing so far, I don't think, but let me reload. I don't know how far along you guys are, but it doesn't have to be overly elaborate, doesn't have to be crazy pants, although more than happy to see you guys do a more elaborate crazy pants version of it. But something like that is probably fine. I want you to think through things. It's the act of brainstorming. It's not going to be polished. It's meant to be a doodle, but doodle it. Right. I'm going to talk through mine if we don't see things soon, but at the same time, I want to see what you guys come up with for how you might want to view parliamentary procedures. Otherwise, I'm just going to turn the whole thing off and just like, yeah, no one gets any points on that one. Yes, I can be a jerk. Okay. So maybe take another minute or two, just fire up whatever you have. If you can't find the link fast enough, or you have an image, just maybe throw in the chat, hey, hold on a second, and I'll hold on a second. Okay, no one submitted a damn thing. So I would like you guys to submit it while I'm talking about it, and then I'm going to turn it off. So here is, I know it's suboptimal, but let's have a quick look at what the heck I'm dealing with. So my thought was, issue you're going to have is if I use, here we go. If I use a map of Canada, what's the issue going to be? It's going to be Toronto. It's going to be some of the really densely populated areas where I will not be able to see every single MP all at once, right? Northwest Territories, any MP that for there, they're going to have a lot of land. There's a lot of space to put that one little dot. But if you're talking about the GTA, no, it's not going to work very well, right? It's going to be a very dense, a whole bunch of points in there. So I would actually like to use the House of Commons. Now, of course, the problem with the House of Commons is you don't know where they're sitting in the House of Commons. That seems, where you live, so you could put maybe your postal code. So type in your postal code, and it'll say who your MP is. But maybe you want to look at other MPs, things like that. Maybe you can also look at a map of Canada and have it interactive. That would also been fine. This is just my brainstorming in there. You can't show a crazy ton of information per MP. So what I was suggesting is you choose your MP, and then on the side you also have maybe a bar graph, maybe some other glyph. Maybe you could do a whole lot of different things. You could do a glyph on here, but it's kind of hard to. You could do basic information, but you can't really drill into it. You can't really filter that easily. The idea would be maybe I have a bar graph. When I click one bar for the bar graph, I get the subsequent breakdown of that bar graph into another bar graph, which again, I can select individual parts, but that bar graph is one number, so it shows up over here. When I click at one of these things down here, I get another bar graph, another bar graph, another bar graph. I can selectively refine it. So it could be all topics, then environmental topics, then selecting one of these points would give me cap and trade, for example, what their voting record has been on cap and trade. You would then, oh damn, great, you're not seeing a thing. Hold on. There we go. So bar graph, select a bunch of iterative refinements of bar graphs, which actually filters, or actually it's aggregate to begin with, and then you're teasing it out as you drill in. So I can get the environmental vote as one number. And then as I tease it out, I can look at cap and trade individually because it'll be subsequent bar graphs afterwards. Once I've done that, then I'm looking at cap and trade. Well, their rating on cap and trade, if I put it on a scale or some kind of ordinal value or continuous value, what I could do is then color in the seat in Parliament. The outline is the fully saturated color, like liberal red, like conservative blue, and the inside is the amount of fill, maybe the amount of transparency I have. So you see what it's compared to, what the maximum value is, and how in line they are with that. If they're doing a lot of, if they voted strongly in favor of cap and trade, to be fully filled in. If they never vote for cap and trade, it would be empty. This is just brainstorming. It might be a stupid idea. That's fine. The point is that it's open. Okay, let me reload it one last time. Hey, there we go. We finally got some people. Thank you. Thank you, everyone, for doing that. Okay, so let's see what we have here. An untitled document. Okay, Andrew, you might want to throw in no images. So come on, throw in some images. I would drop down for the view party preferences and their beliefs. Yep. Search your MP by name, writing, and province. Yep, and you'd filter that. That's you're selecting based on that, but you might also filter everything else out. When you click on the MP, show their party topics voted along. Show info like time in Parliament. Yeah, great. A different version of filtering based on your finding your MP, and then you see that MP's data, and you can also get the overview. Great. Just put your name in the thing. Let's see what other ones we have in here. Guy, we're gonna throw your thing in there. I'm not trying to pick on anyone. Oh, nice. Okay, let's see here. Okay, let me see if I can pull it off that tab, actually. Where's the tab? All right. So click on any colors square to filter responses by the party. Great. So you would have all the party colors. Wonderful thing about Canada, we have party colors that everyone can see and they're associated with that party. It gets really weird, like the block sort of threw things off because there's no longer one blue party. And I think ADQ also threw things off. There's a couple of parties that came in. The People's Party of Canada had to go with purple because no one else had purple. And it was just like, it gets kind of wonky after you get more parties in there. But most parties have a unique color that everyone goes, okay, that's the Green Party. No one else dares try and go green because it shows the Green Party. Okay, lower transparency shows the number of seats that voted. Great. So if you are showing the number of seats that voted for the party. Okay, but then each of the, are you talking each of the seats or how many people in the party voted for that, which you do transparency for, let's say, the Liberal Party and just do an amount of transparency for the Liberals, how many of them voted for that bill. That would be great, right? And but now you need to figure out how you're filled, which of your, what attribute or what characteristic you're looking for. There's too much than just how many times they voted. They're voting on a large number of topics. In fact, one of my personal favorites is every time there's a vote involving you know, distinct societies, all that kind of stuff. Anything that is a hot topic issue that's going to get people into trouble. What you'll notice is the bloc will put forward some legislation or have some kind of vote on, is Quebec a distinct society? And then all the other parties then have to sort of dodge around. They have to figure out how their votes work so that you'll get Justin Trudeau who votes present. He doesn't vote yes or no. He votes present just to not be accountable for what he's voted for. Like that, he doesn't want to get in trouble, but he also doesn't want to say like, yeah, Quebec can make, you know, it'll be a legislation like Quebec can make their own province, and Justin Trudeau will be like present, like that. You'll see that actually happening because they have to make sure that they don't just say, hey, Quebec, go off and be your own province, but they also don't want to say no because then it'll be used against them later on in the next election. And there's all these strategic voting that you'll see along the way for hot topic issue. Cap and trade, same thing. Anything hot topic. Let's see what other things we have in here. I really miss people being able to just talk aloud their ideas here because it works a lot better. Oh, that's nice. Okay. User will be able to hover over any given seat. Will present tooltip showing the MP and what area they represent. The bar at the bottom will allow the user to see who voted for what for which issues. Yeah. So the pipeline voted against for and against. Beautiful, right? You're filtering based on the issue and then representing it on the map. Great. And you're keeping around the party affiliation, which is actually an important part of that. And if you're just filling it in with black, then you can see where the Liberals are, where the NDPs are, where the independents are, and get a sense of it. Love it. Nice. Nice work, Sebastian. That we already did that one. Oh, nice. Okay, individual vote for topics will be displayed in blocks divided by the party. Great. You're gonna vote color of green and against oh yeah. Oh, green and red. There's one issue with green and red. And unfortunately, it's Canadian politics. Well, so you actually have two problems with green and red. Not really problems, but first of all, color is already used for Canadian politics for what party you're involved in. Same with American politics with blue and red. But number two issue, people are red-green colorblind. It's something to just always worry about. There's not one right solution. So it's something to consider, but this is a great approach, right? Green and red for yes and no, great. Works for me. We have oh, sorry. Yes, yes. Our parties have different colors that are associated with them. This is a great example, by the way. This is a great design. So the Liberal parties are red, is always red. The Conservatives are always blue, a particular shade of blue. The Bloc Québécois is a particular shade of blue as well. It's a light blue. The NDP is bright orange. And who am I missing? Green Party is green. And independents normally we do as gray. Yeah. But yeah, there's like 5 colors that we have that we always use, much like Republicans and Democrats in the United States. it allows you to just immediately go like, oh, this person's the NDP party member because all of their signs are bright orange. Nice. I completely forgot about that aspect. So thank you for asking about that. That parties have colors because I took it for granted. A complete mistake on my part. And importantly, if I take that for granted, other users of the system, you might design a system, but other users might not remember or realize that parties have particular colors. If you're talking about any place that has a high immigration rate, Greater Toronto area has a high immigration rate, you cannot assume the people using your system will know about the color mapping, and you will have to do color and say the party and be very explicit about it. These are the kinds of things that when you're designing, you don't know, and that's why you do user evaluations. Fantastic. I also wanted to do one thing first before we do it in a second. Nice. Vote for. What are they voting for? Oh, all right. So it's a straight up list. What are they voting for? Who your member of parliament is, and you can color it in. Great. And now you can filter based on the topic. You can choose your topic in the center. Works for me. Oh, nice. That's just somebody else's stuff, though. Oh, it's supposed to be yours. Who voted for what key issue? It's a great example. It's not yours. It was meant to be your design for how you would do it. It's an interesting approach because here we go. Here's Alberta. It's actually, notice this is a distortion of Canada, sort of squished horizontally and then allowed to extend down because Ontario, just so many people in Ontario, you've extended down away, but your provinces tend to go east-west. And then you can see who the various groups are and what they voted for. It's a great visualization, just unfortunately not yours. Maybe I didn't explain what I was looking for that well. The design is actually like you can look at other people's examples, but making your own, it's what gets the juices flowing. It's what gets you thinking through the process, how you make design choices. So other things here, I don't think I have another one. So let me just do the following. And I don't have that. Viewer. There you go. If people miss the lecture, I might open it up later, but upon request. If you missed the lecture, fine, just let me know. I'll give you access to it. All right. I might miss a couple other ones in there, but so far those are all great. Nice. I am the people that submitted something, I am very impressed. All right. I wanted to get to, I just don't want people be passively sitting back and like, teach me, fill the bucket of my knowledge. It's that's the reason we have these exercises, because until you apply it, it doesn't stick in. It's how you cement knowledge. Okay. I want to talk about trees and networks. I mean, this is completely off the beaten path. So, and I'll go over what we're talking about now, but that was the end of filtering and aggregation. Trees and networks, I'm just going to give you an advantage on the next N2400 and all your other subsequent courses because it pops up, and yet it turns out it's not things that every single person has seen all the time. When I was teaching at Northeastern, people just went, yeah, trees and networks. And I came here and people are like, what the heck's a tree? And I go, oh, yeah, there's some institutional knowledge or some knowledge in our domain that does not necessarily get passed on to people. I meant you didn't learn this in the womb? What? Yeah. So we have to go over it, and multiple exposures is good. But I want to go over the course so far. So what have we looked at? We looked at people, perspectives. We looked at how they perceive things, how they explore data. We looked at the tasks that they're doing. The 3 stars here is because the design process involves iteratively designing and refining what we're looking at. You do not get it right the first time. Nobody does. Don't expect to get it right the first time. None of my ideas are right the first time. No one I know ever has had the right idea the very first time. Some are better than others, but it's never perfect it's never perfect, period. But we iterate to get closer and closer to an ideal solution. The reason I want to put those stars here, when we do your user evaluation at the end of term, that's what we're using, is the tasks you set out. If you said the most important thing to do is to be able to see how much your energy usage in your province is compared to other provinces, if that's the task, you need to support that task. So the tasks you set out, and if you want to change your task, you just let me know. But if your task was, they need to be able to quickly find a skating rink nearby for them to go skating. That's a task. You need to get your users to do that task when you do your user evaluation. That's what we're going to be doing at the end of term, is a user evaluation. You're going to say, here are the tasks you're supposed to do. Here's what you're supposed to do is find a skating rink to go to. Here's what our system is. Don't tell them step by step how to do it. Just enough information to know what their system is about, and then give them a task. If they can't do your task without instructions, especially without step-by-step little minuscule instructions, if they can't figure it out, you did it wrong, right? If it's not quick for them to do it, you did it wrong. Or if it's not doing the task, like if they have to spend 20 minutes to find a skating rink to go skating, it's not an efficient way. So they should know that it's supposed to be efficient for finding a skating rink. If it's not efficient for finding a skating rink, they should tell you. And that's what your user evaluation is all about. You give them the task, what they're supposed to be able to do, either fast or accurately, or get insight about investments relative, that's not a fast task, but they're supposed to get insights about how investments work in the city in the city. So if they cannot make any kind of insights about, what to invest in, or some kind of meaningful reasoning about, some weird trends or some patterns in the data, then you did it wrong, right? That's effectively it. The task is this. If you don't support your task, then you didn't do your system right. You don't get 0 or anything, but that's ultimately, your system is only as useful as the tasks that it's supposed to be doing. Okay, so that's what we're doing for user evaluation later. We've also looked at a whole bunch of design things, including marks and channels. How do we encode data? What kind of, can we encode things with color? Can we encode things with, how do we do filtering and aggregation? Do we have multiple facets of our data? And the big thing that we kept on running back into is we got too much damn data. That is, I should say that the very first class, and I probably need to revamp things a little bit. The first thing is always, you have too much data, figure out a way to deal with that sheer amount of data. Because if it's just like 4 numbers, it's easy. 4,000, that's hard. That's actually the art form that we're dealing with, because as we get more and more data, we don't get like a little pie chart. We get 400,000 things. You're looking at Carleton students and how they're doing, or how they feel about, the survey data about how they're feeling about online classes. It's not one person. It's not 10 people. It's a crazy number. And just taking the aggregate doesn't tell you everything. It hides key information. I need to be able to look at different facets of the data. So it turns out everybody loves asynchronous classes, according to Carleton. Blended and asynchronous, they don't want live lectures. And yet my 1400 class and my 2400 class are saying, oh my God, I want synchronous lectures, right? They're different. Different groups have different needs and different wants. So I want to be able to look at different views of the data, different parts of the data, different facets of the data. So maybe I want to look at satisfaction. Maybe at another time I want to look at the number of grads versus undergrads and their tuition rate, or when their classes are. I might want to overlay data. I might want to have different visualizations at the same time. I might want small multiples. And all of those things involve some kind of interactivity so that I can change my view, filtering out data I don't want, and aggregating data if I want the general overview about what that data is, not all the nitty-gritty details. We also looked at focus plus context, as in I see the overview of all the Carleton students, but I'm only looking at this one subset. But I still get the context so I don't get lost in the data, and I know how this relates to other stuff. So I'm looking at my member of parliament here and how they're voted, but I can see other member of parliaments around the other members of parliament around them to get general sense of how how they are compared to everyone else. That would be focus plus context. It helps aid cognition. And the reason we need to, we're going to look at some visual domain specific things now. That's most of the, all 3 lectures left. We've already looked at storytelling, by the way, so we sort of jumped ahead on that one, and maps. But I'm more than happy to talk about casual visualizations. That's actually my area. I don't have a lecture on it, but I can easily make one. Sci-Viz, how you look at the geospatial information, how you look at like a airflow of an airplane. That's my example I always go to. How do you do dimensionality reduction? That's actually a really big challenge. It's very mathy though. So if you don't want math, we're not doing that one, right? It can get very mathy. I'm not even going to go into the math, but it's still very mathy. We could look at timelines, how we do temporal data. That's its own area. But for today, we're looking at networks and graphs. It's one of the classic subparts of visualization. It's a classic subpart because so many people do research on it. It is shocking that something so simple is so studied, and yet we still do not have a right answer for it. It is, and how powerful it is for something that's so simple. But we'll look into that in a second. I've already discussed sprints, by the way. So the idea of the sprints, but I want to make sure we're looking at is when you're finally done, we want to do a user evaluation to make sure that we actually hit our marks, to make sure that we are on schedule. We have these little sprints, these little timelines where you say, I'm going to do this much this week. And you do that much that week. What you cannot do, and I'll state this again for the record, what you cannot do is think you can make the visualization the night beforehand and hope everything lands. That's why we have those sprints, because I've gone through that problem before without the sprints, and people will procrastinate. And then at the 11th hour, they will try and make a system and it will crash and burn and they'll have nothing to show for it. That's why we have the sprints, to make sure that at least you have something. Keep previous versions of it. If you break the code at the day beforehand, go back to the previous version. That's fine. It won't be perfect. Fine, good enough. The last thing we want is you have nothing. That would be the worst case scenario, because you won't get any points for your evaluation. You won't get any points for your final project. You won't get any points for this or any points for that. You'll lose a whole lot of points. That's the worst case scenario for your project. So we need to do these little sprints to make sure that you have something at least reasonable. If you get stuck, I want you guys to talk to me. That's because people get stuck. They get stuck all the time. Okay. So we were talking about all this, like we have too much data. And I said, we're going to look at domain specific stuff. And we're talking about user evaluations and the like. But the reason we need to talk about there's too much information before we get to domain specific stuff is because this is why we needed to talk about filtering and aggregation and focus plus context and all this stuff. Trees and networks are the classic example of way too much information and our brain not being able to handle it. We have the data. We can actually programmatically use the data, but to make sense of the data, having a human involved to make sense of the data is really a lot harder than it seems. So let's explain what I mean by trees and networks, first of all. I know, crazy. So, and I like pointing this out. I unfortunately said this to a friend of mine. So Dan Archambault is working over in the UK right now. He is one of the world's foremost experts. And it's weird to say that because we went to undergrad together. We went to grad school together. He's from Ottawa, but he's one of the world's foremost experts in visualizing large, really complex networks and graphs. That's one of the things that he does. He's very good at his job. But he was talking about, I'm trying to think here. He was talking a long time ago. He was looking at somebody else's system, and they're doing, bar graphs or some other visualization. I said, what if you made it into a network? What if you made it into a graph? And I was like, don't take offense, but if all you have is a hammer, everything looks like a nail. He's so looking at graphs for everything that he tried to shoehorn other topics to graphs. The reason I bring this up is because we as as computer scientists, as people that are in this field, we see this so often that we apply it to everything way too much. So if you have never seen this before, that's fine. But we get so used to seeing graphs that we forget that other people don't know what they look like. We forget how common, how much of an abstraction they are. So let me try and explain it to you. But being aware that you're probably going to get exposed to it again some other class, because it's so common. It's everywhere when you talk about any kind of programming, any kind of computer science, any kind of IT thing. Okay, so we're going to learn what a network is, like a node and edge. We're going to find the definition of a tree finally. We're going to be doing trees in 2400, and people are going to say, you didn't teach us trees. And I'm going to say, well, what's there to learn about them? They're pretty on the nose, but we'll get to that. We're going to learn common visual coding techniques for networks, like an adjacency matrix, like a node-link diagram. If you've seen this kind of stuff before, I'm hoping there's still something interesting for you guys, but there's a lot of people that have never seen this before. Okay, so we've looked at a lot of these things. We've looked at tables, we've looked at fields, we've looked at geospatial. This is the one we're looking at. It's these little edges with a little dots on them. It is who's connected to who, what's connected to what. That's what a network is all for. And people, at least in 2400, were like, I don't get this. I'm like, what's not to get? You do it all the time. LinkedIn is literally the link between two people. That is all LinkedIn as a thing is. Here I am. This is me. This is Dan Archambault. We are linked together. We have a connection between us because we work together. We actually know each other. So we are a professional. We have a professional link between the two of us. That's what LinkedIn gets its name. It is a graph. It's every person you know who you are linked to. That's that. That's what this is. This is just a visual representation of this. And you'd say, who is a sick person that came up with this visual representation of this? And hopefully it's the next thing. I'll have to, it'll be a couple slides from now. The answer, as it always is, seems to be Euler. Leopold Euler, I think it's Leopold. Euler, he has a name, the E, the irrational number E, Euler's number. He has his name on 1,000,001 things, including there's Venn diagrams, there's Euler diagrams, which is a kind of Venn, it's like a Venn diagram. He's in everything. He's one of the most prolific mathematicians of all time, and he invents graphs on a whim. Like just sort of, I'll just invent this other branch of mathematics. It's willy-nilly. It is great. It's great, impressive. So here's the idea. We can call them network and call them node-link diagram. Well, node-link diagram is a visual representation. A graph is a mathematical graph, not graphics, not bar charts and stuff like that. A mathematical graph. Easier to call them a network. It is people or things and what they're connected to. This computer is connected to this thing. It has a connection, some kind of communication connection between these two computers. That would be a network. The network technology group is doing this. The links, they're sometimes called ties. They're sometimes called edges or relationships. Everybody has a different name for all of these things. But essentially, there's a connection. And then my nodes or my items, they are the computer. The computer's in a network. They are the people that know each other. They are your social group. They are what course is connected to what other course in your degree program. The reason it's that hammer and nail quote earlier is because you can apply it to almost anything. If you have some kind of relationship between two things, you got a network. If I'm worried about who knows who or what's connected to what, you got a network. That's it. So a network is just a graph, how you visually, or it's a way of representing relationships between discrete things. Parents and children, whatever. Discrete as in it's not the same thing represented twice, or a continuous thing. It's this computer, not the two computers are actually just one computer. A special kind of network is called a tree. This is, we normally mean it's hierarchical. It's not in the mathematical sense. For mathematics, it's not actually hierarchical, but we'll get to that. But the idea is like your folders on your computer are a tree. This folder has this folder, which has this folder, which has this folder, which has this folder. Folders inside of folders. It's a hierarchy. Okay, so we have hierarchical information, the CEO, then the vice president, then this person, then the director, then the hierarchy. So something at the top then goes down to subsequent stages. The idea is I have a starting point at the very top, one of them. It goes off to one or more children, child things. We'll also look at this when we look at object-oriented programming, by the way, in 2400. So you have some starting point, you have one or more children underneath you. Those children may have one or more children underneath you, but they never have a cycle. You'll never have this thing being the parent of this thing or this thing being the parent of this thing. It's never cyclic, and there's no connection between the children. So this has children that strictly have children that strictly have children. It's directed, or it's not even directed. It's acyclic and it's connected. So everything's connected up and there's no loops. You cannot make, there's no circle here. If those two are connected, then you get a triangle. You can't have a circle. So I'm not sure if this is a Hall of Fame or a Hall of Shame. I would probably call this shame just because of the clutter. And it's also red, green, and also not color coded based off of what group is in what. Rick Santorum voters, Rick Perry, Republicans, Romney, Newt Gingrich, Herman Cain, Democrats, so Republicans and Democrats, they're showing the connections between positive and negative edges between entities, who complains about whom, essentially. And so if Obama complains about, I think this is, if Obama complains about Santorum, you have a red line. If Santorum complains about Obama, you have a red line the other direction. But it's really, really messy. Like, try and make, what are you trying to read off this thing? I got no clue what this thing is saying. It's who's bashing whom or who's positively supporting whom in 2012. This is way back in the day, 8 years ago or more than 8 years ago. But who's supporting whom, who's complaining about whom. But it's really hard to read. The colors are hard to read, and there's too much information. Now, they did do some stuff. They amalgamated or made this node more prominent to make sure that you could see Newt Gingrich or Obama, because they're bigger nodes in the diagram. But this is a whole bunch of connections between everybody. Really, really fortunate. Here'd be a better version of it. Obama and Romney are color coded based off of who they, what party affiliation they are. You're not using red, green everywhere, which hurts people that are red, green colorblind. And you'll notice that there's a directionality of this. So this is a subset of electoral network color partition. First second value of symmetrized adjacency matrix. Don't worry about that stuff. Expected distinction between Republicans or Democrats. Orange and green links show negative and positive relationships between entities. So Clinton is supporting Obama. Obama is supporting marriage. A lot of surprise, I guess. Romney also supports marriage. A lot of surprise. Romney is attacking Obama. Obama is attacking Romney, not remotely as much. Legal status is being attacked by Romney. Investors are being promoted by Romney. White males, surprise, surprise, I think are promoting Romney. I think that's the directionality. There's a directionality to this stuff, which you can have. It is better in the fact I can see how much someone's supporting something. It's still the same network. It is Obama supporting this topic, or Obama is supporting or being attacked by governors, or Obama is attacking governors. So this is another graph. I think it's a better one than the first one. Or this is even better. I mean, this is in the NBA. This is of 2014. Who is passing to who on what team? How good is the teamwork on your team? Here's Chicago Bulls, right? Charlotte Bobcats, That is some really heavy passing between two players. I'm just trying to think of the Celtics are doing okay. Cleveland Cavaliers are doing okay. I thought I had a better one than this. The Bulls are not doing that badly there. I thought I had a version of it with the Houston Rockets, and the Rockets had this crazy graph. It was just really tightly, all these bands between them. There's an incredible amount of passing on the team, which is one of their advantages. I don't think I have that. But the more you passing, if you have really good team coordination, you don't have these thin lines. You have these thick bands, and you know who's passing to whom at a glance. Graph. Okay. So we're going to talk about network. We can arrange things based on a tree. So in a load link diagram, we have a bunch of connections, and we have a bunch of, so for our connections form our marks. They're a line connecting two things. We also have points representing our entities. Great. That same graph, the concept, who's connected to whom, can be represented with a matrix, an adjacency matrix. So if person 1 is connected to person 2, I color it in. Person 2 is connected to person 1, so I color it in that way as well. Notice this is perfectly symmetrical along this horizontal thing. And so this person 1 is connected to person 2 only. Person 2 is connected to person 1, person 3, and person 4. 1 is connected to 2, person 2 is connected to 1, 3, and 4, presumably. It's the same data, just a different visual representation, giving you a different tool, a different way of looking at it. And then we have one more, one of my least favorite of all time, which is the tree map, but enclosures also work. So this is the top of a tree, let's say. It's really good for trees. It's not really good for networks. It doesn't expand to networks. So this is the top layer. This is the C drive. This is my first subfolder. This is another subfolder. This is another subfolder within that subfolder, another subfolder, and subfolders within that. You're using containment to indicate what the hierarchy is. So there are 3 folders in this folder, which is inside of this folder, which has 2 folders. This folder has 2 subfolders. This folder has 4 subfolders, that sort of thing. All right. Let me get ahead of myself. Hold on a second. There we go. I want to give the sort of the history of this. I told you Euler was the person who invented this thing. This is very, 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 very old. And this also illustrates why we do it all in one go. I always love telling this story. I probably tell it wrong. So the 7 bridges of Koningsberg, if I'm pronouncing that right, those 7 bridges don't exist anymore, but it is one of the classic, it would be like a mathematical, like travel vacation, like a vacation, like you go there to see the bridges. Oh my gosh. Like I went to Avignon to just walk on the bridge, just the Pont d'Avignon, because why not? There was a town, Koningsberg, still exists. I think Russian, can't remember. They had at the time 7 bridges. The local tourist board, as it were at the time, I guess, what the thing was famous about the city were these 7 bridges, and they wanted to have some way for tourists to visit all bridges and come back to where they started. So they walk like a walking tour of the town. Pretty simple. And you can get people to stare at this thing, work on this. And they, at some point in time, they, given up on people just brute forcing this thing. And they go up to Euler and they say, can you come up with some kind of path across all of these bridges? So you travel across each and every one of these bridges and then go back to the starting point. That's the plan. That's the plan. And you might say, okay, so what did he do? What's so special about this particular problem? What's special about this problem is that, do you need to know what this side of if the task is you need to travel across all bridges and go back home afterwards? Do you need to know anything about the town up here? No. Do you need to know anything about this big landmass in the middle? No. I don't need to know if there's a gelato place or something like that in there. I don't need to know anything about it. How about this ring right here? No. German, thank you. It's Prussian, okay. Nice. Thanks, Andy. Nice. If you want, I'm not going to read. You can read in the chat. There's a great, that's fantastic to know. I always forget. I think I looked it up at some point in time, just memory. Because it doesn't matter what town it is. It's interesting that it comes from an actual example. But, Kaliningrad. Okay. I got to visit that at some point in time. I love Germany. Okay. But it doesn't matter what's on the north shore of this bridge. It doesn't matter what's in the center island of the bridge. It doesn't matter what's on the south. It doesn't matter what's over here. The point, the big takeaway, and the big, aha moment is, what if all I need to know is how things connect to one another? I need to know that I can go from here to here. I can go from here to here. Those things are connected twice. I can go from here to here. Those things are connected once, right? I can go from here to here and then over to here. That's also fine. But it's just it's a representation. Hopefully I have the thing in here. Let's see if I can get a pen. I'm not sure I can do that properly. The point. Let's see if I can just talk it out. What if I put a big circle here? And I put two lines between, I put a circle here, I put a circle here, and put two lines in between. I put another circle here and put two lines in between. They're connected. I am taking away all the geography. I'm taking away everything else other than the connections, because the task is I have to traverse, walk across each of those bridges. So I have to go along an edge. I have to go along one of these lines, these links. I have to touch every single one of these lines and then go back to the start. Take away all the other things. All I care about is the connections. I'm abstracting out all the other details. In fact, I'm not 100% sure about this, by the way. So I'm saying it like I'm confident in it, but I'm pretty sure it has to be this way. Every one of your GPSs is doing this. I know your networks are doing it. Every time you're rerouting traffic, it's doing this for sure. Like network traffic on your computer is doing this. This entire lecture is based off of networks and graphs, because I'm sending all that information across a network, and it's only being done because it knows how to properly manage a network of traffic on the internet using a graph. Turns out your GPS, if I'm trying to travel from point A to point B, all I need to know is where the intersections are and how long, how much distance or how fast it is to go from one intersection to the next intersection. And now I have a network. I don't care if the road is curvy. I don't care if it has a bunch of bumps in it. The only thing I care about is the distance for you being there and that intersection if I'm trying to find the path between a bunch of points. It is traversing a graph. I don't care about all the other details. It doesn't need to know about the map of Audible looks like to find the traffic. That's why GPSs work anywhere. I just need the network, and the same algorithms work for all cases. That's why we do it, because you can ignore everything else. I just care about the network. So this is one node. It is connected to three edges, to two different nodes. This node here is connect as two connections to this node, one connection to this node, two connections to this node. This node here has two connections to this node, one connection to this node. What turns out is Euler then did a mathematical proof, didn't even look at the bridges anymore, and proved in general that if you have an odd number of edges, you cannot do a tour. You just can't do it. You can mathematically prove it. Done. There's no point even trying to do it. If you have 7 bridges, or if you have 13 bridges, or 53 bridges, you cannot do a tour. Done. Okay? Way more general. And more importantly, it leads this entire branch of mathematics of forget all the nitty-gritty details. If all I care about is connections between things, now I have something interesting. Okay, so here is what a graph looks like. A graph is a graph G. Let's do the mathematical version of it. A graph G consists of a collection of vertices. You got a bunch of circles. You got a bunch of items. We call it a collection. We're going to call that V, for the set of vertices, and a whole bunch of edges, a set of edges, E. Okay, you got some edges, you got some vertices. They can connect up. An edge connects two vertices. Sometimes it can connect itself, if you want to look at it that way, but well, let's pretend that we don't have that. So an edge connects two vertices. Okay. And so here is a graph. So here is a vertex. My vertices here are 1, 2, 3, and 4. My edges are 1 connects to 2, 1 connects to 3, 2 connects to 3, 3 connects to 4, 4 connects to 1. Now, I'm going to wait for you guys to give me an answer here. Which of these graphs is represented by this set of vertices? They all have 4. Okay, fine. But which of these graphs, 3 graphs here, is being represented by this? Wait in the chat. Please someone speak up after we wait here for a while. Oh, you're right. You're right. It's still part of Russia, but it was part of Germany. Okay. Euler actually worked in Germany. Sorry. I worked in Russia. That's actually where he worked for the Tsar back in the day. So I assumed it was Russian. Okay, German. Cool. But then I means he had to go to Russia to visit it. I don't want to go to Russia. Well, it's more the I say a lot of things. I'm afraid of getting into trouble. Hey, going down to the States gets me in trouble from time to time. My wife got, they took away her work authorization at the border one time because I don't know why, on a whim. And every time we cross at all, they grill us over it. So going to Russia, it sounds even more dangerous. Yeah, we're Canadians and they don't like us, by the way. Yeah. All right. Canadians with jobs at American universities, no less. So which one of these graphs is it? Oh yeah, yeah. I don't have an American passport. I have a Canadian passport. I'm Canadian. I was working in America, but under NAFTA rules. And yeah, they I think they sort of didn't like her face one day, and it's all it's on the whim of the border guard. So it's sort of weird because she's managing people. Oh, you're not allowed to manage people under NAFTA rules, and yeah, she had to cross with a lawyer. It was a whole thing. All right. So which one of these is this graph? I'm waiting for you. I'll give you a hint. You can. I think you cannot be wrong. There's one way to be wrong. So graph one, graph two. They are all the same. Very beautiful. Nice. Thank you, Kara. Yeah, they're the same damn graph. They look radically different. They're the same thing. That's the point I was trying to make. So thank you very much. That's the point that I'm trying to make here. I can visually represent the same graph multiple different ways. And now my question is, what's the right way to maximize my ability to look at it? That's why so many people spend so much of their time studying graphs in the visualization community, because we have these crazy complicated networks, and yet there's no one right answer. The spatial layout is by choice. You choose the layout, or you have some algorithm to choose the layout for you, but it's not part of the data itself. It's much like the rest of a lot of the other visualizations. I'm choosing to use a bar graph instead of a line graph because I think it's going to be better for perception, but it's a design decision, and I can evaluate the design decision, how the quality of my layout. Graphs, there are some better graphs than others, but it's a design choice of how you do it. Okay. So there's that, because we're trying to just get the heck out of the way of that design. So we have a couple other little subparts. We're going to have another lecture on graphs afterwards as well. But we have a directed graph. This is actually what we would expect most GPSs to be using. This is what I definitely expect your network to be using. It's going to go one step further than that, actually. But a directed graph is I send like your downstream versus your upstream on your computer, it's directional. I have one stream going up, it has a particular speed, and I have a connection coming back to me has a particular speed. If you're talking about friendships, you would hope it would be non-directional, as in, if I am your friend, you're my friend. May not be. And if that's the case, then you have a directed graph. If you have somebody that is clinging on to you and says they're your friend and you're not their friend, that's a directed graph. It's one directional. And you can have both directions in there, that's fine. But if it's not guaranteed that it's both directional, then you need a directed graph. This is an undirected graph. There is no arrows. Great. This is a weighted graph. You can actually weight the vertices themselves. You can weight the edges. A network for computers would be this kind of thing. How fast does it take? How fast is a single packet? Or does it take a single packet to go across the network? Or how many packets I'm sending across the network in a second? Whatever the measurement for speed is. A graph for a highway would be the same thing. How fast can I drive that highway with the distance and the speed I can travel? How long will that take to travel from here to here? That is how I can figure out the fastest route from Canada to here, because I figure out the speed I can travel, the distance I'm traveling, so how long it will take me to go from here to here, and every intersection, or like when I get off the highways intersection, anytime I can go to another road is one of these nodes. And I'm just trying to figure out the weights all along that path. What's the shortest path to go from here to here? There's algorithms for it. Dijkstra's algorithm is one of them. Okay, Floyd Marshall is also one. This is an unconnected graph. I have one that's not connected to other ones. Those are bad. Well, they're not bad, but normally we expect a lot of connectivity. If something's completely cut off, what happens? The person lost their internet connection, not on the network. The degree, this is actually where Euler's theorem, well, some of the Euler's theorems come up. What he did with the bridges was this. He figured out the degree for each one of these nodes. So the number of connections to other nodes. So this has 2 connections to another vertex. It says 2 connections. It says 3. This, so 1, 2, 3. This only has 1. It's only connected to this one. The degree of each vertex tells you something. Turns out if you have an odd, you have to, the sum of all the degrees, when you add them up, has to be an even number. That's the proof in itself. I think that's 4, and that's not even 4. Anyways, the point of it is that tells me something, because if one of my computers in the network has a degree of 40,000 and this has a degree of 1, that 40,000 is a bottleneck. If that thing goes out of commission, bad things happen. It tells you how busy that thing is. We'll get to another example of that, I think, in a second. Here's a cycle. Definitely can't be a tree then. Any cycle means I can go from here to here to here. I can also just loop around a bunch of times. Cycles come in handy in the, they can be big problems sometimes. They can also show who's really connected to who forms a group that they all know each other, that sort of thing. This is acyclic. It's also disconnected, but there's no cycles. There's no circles in there. A connected acyclic graph is what a mathematician would call a tree. It just means it's a graph where I have no cycles and everything's connected to everything else. So a tree. And I'll go one further than that, because this is how computer scientists think the world. A rooted tree. So I have a top node, a root node of this thing. If I look upside down, looks like a tree, right? Except it's this way around. My rooted node, I have something to start the whole thing going, the root node, and each one of these has children, and they have children, they have grandchildren. A leaf node is like a leaf of a tree, has no other branches from it. So the root of the tree, then a branch, like a tree, the branches of a tree. They don't call these twigs, they're called still branches, but that's essentially what you're doing. It's the metaphor of a tree. Upside down tree, but a tree. Okay. So that is what a rooted tree looks like, which most computer scientists just call a tree. It is so common that we don't even think that you don't know this. Like when I first started talking about trees, people are like, what the hell is a tree? And I'm like, what do you mean, what the hell is a tree? It's a tree. Why wouldn't you know? Because it doesn't naturally come up, but we see it constantly. You'll see it in all your other classes. Every time you do any kind of other programming class later on, you'll see trees. Anytime people talk about things, they'll talk about networks and graphs and trees, not just for the network technology. You'll look at network diagrams when it comes to meshes, when it comes to, and graphics, for example. You'll actually be doing pathfinding algorithms and find networks come up when it comes to computer graphics. It comes up when it comes to rendering. It comes up when it comes to, well, from a social network, you can actually look at graphs and trees as well. And by the way, we also have another number here, not just the degree. You could say the depth of the tree. The root as depth 0, as the start. When the child of that root node, depth 1, then 2, then 3, then 4. It's kind of important because if I'm designing, let's say, the menu of a interface, I worry about the depth of the tree. A menu like like the user menu for any of your programs. I have file, home, insert, draw, design. This, I'm looking at PowerPoint right now. That's a menu, right? I have a root. I have a whole bunch of children. One of them is file. One of them is home, insert, draw, all this. And each one of those has a bunch of other fields. And this has another bunch of fields. A menu forms a tree. And knowing the depth of the tree tells me, is it too deep? Will I be able to find that item later? That's actually, you can actually do the analysis for your menus when you're designing a user interface using a network to make sure that it's not too deep. Okay. Let's see. Our primary concern right now is the spatial layout because we get to choose this. We have this data, things are connected. How do we show it so that people can understand it? And our idea is to depict the graph, laying it out like this way. But we have to show connectivity. Oftentimes we need to show the path, like when we're trying to traverse a tree or finding one place to another. Sometimes I want the network distance, like if I'm doing a network diagram. If I'm doing how connected I am to another person. And I want to see who works together. Do I have a click or clique? It depends on how you want to pronounce that word. I think I just read it all the time as a say clique, but it's click. Right? A social group that they all know each other. They all really tightly connected. That would be one of those. But everyone's connected to everyone else in that. Those are important to point out. If you have a computer network, that's a computer network that's highly dependent on each other and stuff. Do I have an ordering? Do I have a hierarchy in there? And I oftentimes want attributes and tasks. So I'm going to, let's see here. We're going to get to that in a second. I want to point out one thing, and then we're going to stop and we're going to pick this up next time around. Quantitative data, texture, connection, containment, and shape. Stuff they think. But that's not what a network diagram is. Network does not use this. We'll have ordinal data and we'll have nominal data. We want to know this person is connected to this thing, but there's not really like a continuous range in there. So look at it. Texture, connection, and containment and shape are all pretty darn good up here for nominal data, the stuff that we want a network to be showing. And that's why it works so well. That's why network diagrams don't have to worry about space that much, although position is highly important, and why we try to make sure that the position works correctly, even though it's not being encoding anything in the network. So when we're talking about this, we'll be seeing Gestalt principles of grouping, proximity, and connectedness. And when we come back next time around, we'll do an in-class exercise involving, hopefully I can just show it to you. We have all sorts of things we can do here. This. We're going to just doodle up a bunch of graphs and see who has the craziest but accurate graph that you can come up with. Okay, so with that, I'm going to take a quick break. We're going to come back, and I at least have one group that I want to talk to that wanted to talk to me as well. But if anyone has work on their projects, we'll form little breakout groups, and I'll just help people with their projects during lab time. Okay. All right. So thank you very much, everyone. And I will talk to you next Tuesday. Ask questions if any pop up, and I'm just around for the next 2 hours.